Okay. Should be on the recording now. So I saw most of your final project proposals, and I guess for now every group is okay. Some of the group might have easier topics for a three people project, but I think in general it's okay. We will email you the details if it's really not okay. If you don't get any emails or something, it means it's already approved. It's fine. All right.
By when?
By tomorrow, I guess.
Okay.
Yeah. Okay. So today is the second part of the finite element simulation on deformable objects. Still, it's on famdefault.org. It's still following Professor Aptikus Safakis notes. Okay. So let's get started. I guess you guys haven't forgot the thing that I talked on Mondays, but still let's get a recap a little bit. So in last class, we have measured the deformation of an object by using the deformation gradient. So say that if I have an arbitrary object, it's like a bunny shape, and under some deformation function phi, it goes to a deformed bunny shape. We're mainly measuring the deformation phi function by using its Jacobian f equals to the gradient of phi, using this deformation gradient to represent any point here and map it to here. It's already linearized, so phi can be written as an f multiplied by x plus some translation that we don't really care. All right. This is a deformation part. And also, we have lots of models to measure the strain and energy. So we have really different models, like the linear elasticity model, correlated linear elasticity model, the Vanant-Kirchhoff model, and the Neo-Hookean models for that. And we know some model properties that we may or may not want. So for example, there is one property, rotational invariant, that we really want because we don't want to introduce rotation as our extra energy. Rotation should not cost any energy. And isotropy, maybe it is the property that we want, maybe it's not. It depends on really what kind of material that you are simulating. If it's a jello cube, it's perfect to simulate an isotropic model. If it's any other model that's more complicated, it might not be a good case. And also, we want our simulation to be volume preservative. So the main idea is to get the determinant of the deformation gradient f equals to 1, or as close to 1 as possible. But we know that determinant of f is really a nonlinear function, so we really want to make it a linear. So we linearize it in locally to make it something like the trace of f equals to 3, or trace of f minus identity equals to 0. So this is basically the linearization of determinant f near determinant f equals to 1. So we are having this constraint. We add this constraint into our energy to get a full model. All right. So we have a summary of different models. So basically, when linear elasticity, we are measuring f minus I as the strain. And of course, this model is not rotational invariant, and also this kind of energy density do not preserve any kind of volume. And then we have a better model with linear elasticity with small string tensor. This string tensor is invariant under very small rotation. It's not globally rotational invariant, but under very small rotation it is okay. And this energy, because we are adding the second term onto that, it better preserve the volumes. And also we have the Kirchhoff model. This one is a higher order one. It's rotational invariant, definitely. But it is also reflection invariant, because you can have F to be in a reflection matrix and E will not be changed again. And also because this is a higher order function and it has multiple local minimums. So when F equals to identity, this energy equals to 0. But when F goes to almost zero matrix, the energy got another local minimum. So under simulation, if you compress it a lot, over a threshold, maybe like 58% of the original volume, and then the the element will just collapse into one point because it wants to go to another local minimum. Co-rotated linear elasticity, we are using sigma, which is the sigma comes from the singular value decomposition, and minus identity. We want this one to be as close to 0 as possible, and of course we can have the energy density function reading as this one. The problem of this model is it's also isotropy, but if a material is isotropic, then it's perfectly fine to apply this model. And also you need to apply singular value decomposition on every element on every iteration. It's a little bit more time consuming than the model here and here, because they are just the polynomial models, and you can simply add model reduction techniques onto that. And the last one is neo-Hookean elasticity. I was a little bit wrong last week, on Monday, because on Monday I said I1 is determinant of F transpose F. Actually, it's trace of F transpose F. So it was wrong in Monday's class. And it's measuring the trace of F transpose F and the determinant of F as the measurement. And you can write down the energy density as something like this. It's more complicated. This one is nice because it's also inversion free. If the element got inverted, then the determinant of F goes to negative, and then the log of J just explode to infinity. So it can mainly help you to not invert any of the element, but you will get some numerical error if some of the element is squeezed really a lot. And if it's close to 0, then the log of J just will go to infinity. Newton's method will not help you on solving the system. All right, so this is basically the contents of last class. And before I really want to start today's class, I'm also going to get you a warm-up of some linear algebra stuff. The first thing is, let's think about a function f. F maps a 3×1 vector x to a 1×1 scalar, and so f is a function that maps from R3 to R1. It's really common to see when you define an energy on a point in a space, and it basically maps a R3 point to an R1 function. All right, and also now let's think about x. X can also equals to another function, which is g function, that maps from a scalar to a vector. So the g function is a function that goes from R1 to R3. You can think of like if I have a 3D space and I have a trajectory which is dependent on time, and then for each time I should have a 3×3 vector x, and it is the dependent on time. I can write it down as here. All right, and now I have a composition between f and g function. Say I have an h function. It's a function of t. It's f compose g t, which is to say it's f of gt. All right, and we want to compute what is the dh dt. So if those two functions are really simple, I can just couple them together and calculate the derivative directly, because it's just a R1 to R1 function h. But if both of g and f are more complicated and it's really hard to compute them once, we can apply chain rule. to say I can compute the h over, I can compute df over dx first and multiply by dx over dt, where actually x is x equals to gt, so it's more like dg dt. All right, and we know this one is a vector. it's a gradient of f. But in 3D space, you can say it as a 3×1 vector. And this one is also a 3×1 vector. This one is basically the dot product between them, or we call it a contract. So let's get a simple example of this. If fx equals to something really simple in energy definition, like 1/2 of x for Frobenius, no, not for Frobenius, no, it's just 2 norm. All right, and the gt, x equals to gt, and it's a trajectory that I define in 3D space. It can be like 1t, 2t, 3t. It's a line, like a line pointed towards this direction. All right. So one thing is this is my example. H function is simply f compose g. If I can write down it explicitly, it will be 1/2 of this vector 1t, 2t, 3t squared, and it's 7t squared. It's a simple function, so I can just substitute it inside. And then we should be able to know that dh dt is just the 14 multiplied by t, right? Or we can do it then this way, because that we know that dh dt equals to df dx contract dx dt, and we know that df dx is what? Is just x, right? And let's dot product dx dt, which is 1, 2, and 3. And we know that x equals to, just substitute it inside, 1t, 2t, 3t. And after the dot product, it's still like 1, 2, hopefully I'm not doing it wrong. Yeah, it's 14t, and they're the same. So this is how you apply the chain rule on this type of function. Or things can get a little bit more complicated. Say now f is a function of a matrix, like matrix x. Sorry, the uppercase x is also overloaded. It's a matrix of A. Right? A is a 3×3 matrix, so f can be seen as a function maps from a 2D R3×3 space to R1. Why are we caring about those functions? Because if we want to map our deformation gradient to the energy density, it's exactly those kind of function. It maps a 3×3 matrix to the energy. All right. And also, we can define another function, A equals to something like gt. And g is a function that maps from R1 to R3×3. It can be an arbitrary function. And think about it. Think about our discretized case. If I have an element at four points, 1, 2, 3, and 4. And we know that the deformation gradient f can be written down as something like ds multiplied by dm inverse, where dm is the rest shape edge matrix and ds is the current shape matrix. So ds can be seen as x1 minus x4, x2 minus x4, x3 minus x4, and dm is the same one, just applied on the rest pose. It's constant dm inverse, right? So now we can say that f is also a function of x1 if I fix x2, x3, and x4, just to fix all those 3 points and just move this point. And to be more specific, it can be seen as a function of x1 on x direction. So if I move this point on x-axis a little bit, the deformation gradient should be changed. And it is a function of x1, 1. The superscript means x and y and the z-axis. All right. So now this g function can be seen just as this function. It maps from R1 to R3 by 3. Okay. And now we want to calculate another function, h, is the composition between f and g. It's a scalar to scalar function. It's h is just an R1 to R1 function. But if we want to get dh, dt, we can use exactly the same way. We can use df, say a, double contraction dA dt. This double contraction is nothing but just like the dot product in this 1D vector. But here it's like because df dA will be a 3 by 3 matrix, and dA dt will also be a 3 by 3 matrix. It's just a piecewise multiplication. If double contraction between A and B simply becomes 1 less than I and j less than 3, aij multiplied by bij. Just the sum piecewise just multiply them piecewisely and sum them up. All right, so this is a double contraction, and we know we can do it this way. Okay. The second part of linear algebra that I want to cover is something that was missing in the last class, because in the last class I mentioned a lot of stuff about singular value decomposition, and this is decompose A equals to U sigma V transpose. It's a special type of singular value decomposition graphics. Both U and V are rotation matrix, and the sigma is allowed to be negative on this last element. And I mentioned something like polar decomposition, which is A equals to R multiplied by S, where R is a rotation matrix and S is a symmetric matrix. All right, and in the so one thing that I want to mention is it is really easy for us to use a singular value decomposition as a tool for us to compute the best fit rotation R and the symmetric part S to do the polar decomposition. Because once you write down A equals to U sigma V transpose, I can snap a V transpose V inside, because V is an orthogonal matrix, and I can simply snap this identity matrix inside. Right, because this one is just identity. And then it becomes UV transpose multiplied by V sigma V transpose. And set it apart again. This UV transpose is basically our best fit rotation. And this V sigma V transpose is a symmetric matrix. So this is how we get from a singular value decomposition to a polar decomposition. It's really easy. All right. Okay. So after we get all the things that we need for today's class, I'm going to officially start the second part of finite element method in simulating deformable objects, FEM2. In today's class, I'm going to cover mainly 3 parts. The first one is the first Piala-Kirchhoff stress tensor. And then I will do a discretization over the entire space, so you can start your simulation, and we will compute the force and at least cover the explicit time integration. All right, so let's start from the first one. The Piala-Kirchhoff stress tensor. We know our energy definition. There's an energy density function, psi, which is a function of F. And you can pick one of your favorite model. You can pick the like linear elasticity model, or the Werner-Kirchhoff model, or even a Neo-Hookean model, or correlative linear elasticity model, you have that energy density defined over here. All right. So one thing is we can define the energy density explicitly and calculate this thing, d psi over df, and we define this one as our first Kirchhoff stress tensor. So one thing is, what is this P? Is it a scalar or a vector or a matrix? Yeah, right. It's a matrix because psi is a scalar function and f is a 3×3 matrix. All right. So you just take the gradient of this one and becomes a matrix. And if you define your psi explicitly, you can simply get the matrix by taking the derivative. Or someone tends to have this Kirchhoff stress tensor explicitly, so you can just have the psi by integrating this f over function f, integrating this stress tensor over function f. Think about it. Think about a really okay. So what does this p mean? It can be seen as the derivative of psi over f. All right. So let's think about it. If my deformation gradient is something that starts from my identity matrix and plus some really small deformation, so it's close to its rest pose. And what is the energy of f? And psi identity just equals to 0, and I can use the to plus the polar Kirchhoff stress tensor double contract df. If this df is really small, something like if I just move it on the first element, df will be some epsilon and 0, 0, 0, 0, 0, 0, 0, 0, and then this will be my function. All right, so this stress tensor can be seen as a tensor if you perturb your deformation gradient, and at some part, how will the energy react on this perturbation? Right, so this is basically the idea of why you are taking the derivative of this. And so, for example, if I have my my linear elasticity, the simplest one, simpler is always better, which is defined as f minus I for Benio's norm squared. Okay, so I can simply take the derivative of this one. It becomes a k multiplied by f minus identity, and it's a 3×3 matrix, and this is the PLR Kirchhoff stress tensor for this type of energy density. All right, let me fill it up here, f minus I. Or I can have a slightly more complicated one. If I have my this is actually my favorite. My favorite correlated linear elastic energy, sigma minus I for Benio's norm squared plus 1/2 of lambda trace square sigma minus I. This one is definitely more complicated. All right. So let's think about it. Let's think about if we perturb the energy a little bit. What is the total derivative of psi? It becomes mu multiplied by epsilon, sigma minus I, and double contraction d sigma, and plus there's 2 lambda trace of sigma minus I multiplied by let me get my cheat sheet. By trace of d sigma. And here d sigma is a little bit problematic because we want something that eventually becomes the derivative of f. All right, so that matches our definition, but not this one. So we are thinking, okay, what is sigma? Sigma comes from the singular value decomposition. F equals to U sigma V transpose. Right? And if we perturb the deformation gradient F a little bit, dF should equals to du sigma V transpose plus U d sigma V transpose plus U sigma dV transpose. Something like this, because you can just think of U sigma and V as three separate variables and apply the properties of the derivative. All right, I can multiply U transpose and V on both sides of the equation, so it becomes U dF V transpose equals to U transpose V, U transpose du sigma, and V transpose V goes away, and here it becomes d sigma, and also there this is sigma dV transpose V. Okay, and what is this one? Because we know that U is an orthogonal matrix, so U transpose equals to identity. All right, so that means if I perturb U in this orthogonal space, then U multiplied by delta U transpose plus delta U transpose, it needs to equals to 0, because whenever I perturb it, as long as it's in this orthogonal space, it should always equals to identity. So there is no reaction on the right hand side. That simply means that this matrix U delta U transpose is a skew symmetric matrix. All right, so it's U delta U transpose equals to negative U delta U transpose. All right, so this one is a skew symmetric matrix, and also this one is also a skew symmetric matrix, and I can prove it in the same way. Then the product between a skew symmetric matrix and a sigma, which is a diagonal matrix, will have no effect on the diagonal element. Right? The diagonal element should always be 0, because the diagonal element here is this one skew symmetric, this one the diagonal matrix. All right. So that I can say that d sigma should be the diagonal element of this one, because U transpose dF V. Because both of this guy and this guy do not have any effect on the diagonal elements, so the diagonal element here should be the diagonal element here, and we know that this one is a diagonal matrix. All right, so let's think about this one. Double contraction. Here another funny thing comes again, because this one is also a diagonal matrix, so the double contraction will only taking care about the diagonal matrix here. And or if I plug into this matrix, I only care about the diagonal elements, and anything else is not counted. It's sigma minus I double contraction U transpose dF V. All right, and the other thing is here it's also the same thing. I only care about the trace of d sigma. So the trace of d sigma should be the trace of d this one, because their diagonal elements are the same. The trace of U transpose dF multiplied by V. All right. So here, double contraction. If I have a matrix A, double contract a matrix B, it's actually a piecewise multiplication, and you just sum up together. I can also treat it as the first row multiplied by the first row of B, sum them together, and the first row of A, second row of A, second row of B, multiply dot product and sum together. All right. So think about this one. Think about A multiplied by B transpose. A is still this matrix, and I just transpose the B. So this one will be the first row and the first column of the B matrix, B transpose matrix. All right, they are exactly the same, and that one becomes the first element of the sum of the multiplication of those two matrices. And also I can do the second diagonal element. It becomes the second row multiplied by the second column in B transpose. So A double contraction B is simply the trace of AB transpose. So I can put this trace trick inside. It's 2 mu multiplied by trace of sigma minus I, and here I'm gonna transpose it, which is V transpose delta F transpose on U. All right, and plus the second half I'm not writing down over here. Let's think about the first half first. Because this is a trace, and the trace has a cyclic permutation invariant property. If I move this U to the first element, it should not be a problem. It becomes 2 mu multiplied by the trace of U sigma minus identity V transpose multiplied by delta F transpose. And we can expand it back into the double contraction form again. It's U sigma minus identity V transpose double contraction delta F. This is nice because we already separate the delta F with the rest of the world. All right, we can do the same trick here. Here it's basically saying that it's lambda multiplied by trace epsilon minus I multiplied by, I'm going to move this V to the first one. So it becomes a trace of UV transpose multiplied by delta F. And we know if both of them are square matrix, and a trace of A transpose B should be the same of trace B transpose A. You just transpose the entire matrix and apply the cyclic permutation law. All right. So that one becomes lambda trace sigma minus identity multiplied by UB transpose double contraction delta F. And I'm going to move this UB transpose forward. It becomes then trace of sigma minus I multiplied by, what is UB transpose? This is a best fit rotation, right? And multiply, double contract dF. And now everyone is out. This one, the second part, this one is the first part. So we can just simply write the PLR-Kirchhoff tensor as 2 mu. This one becomes F minus R because U sigma V transpose is F, U I V transpose is R, plus lambda trace of sigma minus identity, double contraction F. And that goes back to the definition of the PLR-Kirchhoff tensor. This one, oh, there's an R missing. All right, and this one is my first PLR-Kirchhoff stress tensor. Right. So usually you don't need to come up everything with yourself by yourself and just taking the derivative of those complicated energy to the PLR-Kirchhoff tensor. And usually there's a definition on either the energy or the stress tensor, and most of the people will just prefer to apply everything using this stress tensor. And I'm gonna just write it down: 2 mu F minus R plus lambda of trace minus I multiplied by R. This is my stress tensor, and if you Google it or if you search it on Wikipedia, you can find a stress tensor for all kinds of those models. You don't need to do it by yourself. So for like a St. Venner-Kirchhoff tensor model, the stress tensor will be F multiplied. I'm just copy it down from the book. Lambda multiplied by trace of grain string tensor multiplied by identity. Also, this small string tensor one is the same. It's 2 mu epsilon and plus lambda of trace epsilon multiplied by identity. This one is a little bit more complicated. It's mu multiplied by F minus mu F inverse transpose plus lambda of log J F inverse transpose. So those two things, energy and the stress tensor, you only need to do once, and you can derive the other one either by yourself or just the search on the internet. Okay. Why we care about the stress tensor? Because we already have the energy. The stress tensor seems really complicated. This is because when we want to discretize the entire space and when we want to compute the force and when we want to do the simulation, the stress tensor can be really useful. Okay, so now let me talk about the second part of this class, the discretization.
Hold on, isn't the stress tensor also pushing out from whatever the surface is?
Yes, yes, yes. Right, because
so that's kind of what's reshaping your deformed function, right?
Like if you see this example, if I move the F a little bit by this dF, and the energy actually goes larger because it's the same direction when it's pushing it to the largest energy direction actually. All right. Yes. Yes. Okay, discretization. So the first thing we have already covered actually in the last class is the discretization of the energy. But let me redo it in a more in a more physically correct way. Think about this bunny still. If I have a 3D bunny, although I'm drawing it on 2D, the rest shape is omega. Under some deformation map phi, I'm gonna deform it to a highly deformed bunny. Okay, and what is the density actually? The first thing, what is 2.1 energy? Discretization. So we know this is it's a continuous material. So the energy is actually a function of the deformation map phi, and this should be the integral over the entire domain omega, and this is the energy density phi psi. This is a function of F, and the x. This is the most correct way to represent the energy. Just the integral over the entire domain to see how every point has their energy density goes, and just do it in a continuous way. All right, and but actually we can, in our simulation, we are discretized it into small elements. For this element here, under the deformation map phi, it becomes like this element. And if we sum all the elements together, it also should be the total energy. All right. So let's say this element is I, and my E phi can be also defined as the sigma over I goes from the 0 to the number of the elements. And let's integral omega I, which is this space of psi f I dx. Here I'm still treating the deformation gradient inside this element as a function of f, and it is changing in this domain omega. All right. So let's have another assumption, which is a piecewise linear tetrahedral elements. So what is that assumption? That assumption is saying that inside each of the element, inside one element, I'm going to represent my deformed vertices x equals to phi uppercase x equals to deformation gradient multiplied by x plus some translation. All right. So there are actually two parts in this assumption. The first part is it is a pure linear transformation. For us, we only care about like the rotation, the scaling, and also the translation. So it's just a linear transformation. There's all the degrees are not coupled together. And second one is f is constant within one element. F is constant. Because we are discretizing it in really small pieces, we can assume that inside each piece, the f is constant. And I think it's a fair assumption for a simulation. And after that, we know that we can compute f equals to ds multiplied by dm inverse, where ds is this x1 minus x4, x2 minus x4, x3 minus x4. And the dm is the same thing, it's the edge matrix in its material space, in its rest pose. x3 minus x4. Alright, do you still remember how do we get this one? I think so, alright? You can just write down x1 equals to f x1 plus t, x2 equals to f x2 plus t, x3 equals to f x3 plus t, x4 equals to f x4 plus t, and subtract the last equation by the first three ones, and just represent it in a matrix form, and then we directly get this one. It's already under this linear, piecewise linear tetrahedron element assumption. And okay, so after we have done this, the energy can be further simplified. So now the energy is something like this. Sorry, I equals to 1 to m, and omega I b f I dx. And then we know that fi is constant inside this domain omega I. All right, we can write down it as just to get it out of it. It's phi fi. Okay, there we go. It's phi of fi, and put the integral inside. It's omega I dx. And what is this one? It's this one is just the volume, because you just integrate itself by function 1, and this one is just the volume. And we write down it as wi, something like the weight of the element. So the larger volume the element have in the rest pose, then the larger weight it should play in the total energy. All right. So now my total energy is really simple. It becomes I goes from 1 to m if I have m elements, and this becomes wi multiplied by phi fi. And we know that fi is piecewise linear, it's constant inside every element. One element had one phi. And okay, so this is our energy. And now when we have the energy, we should be pretty confident to do our simulation, because we know the force is basically, because this is potential energy, force is a negative gradient of the energy. Okay. Force. So ideally, one vertex is usually being shared by lots of elements in its neighbors. And you can see each element is pulling this vertex into different directions. So they have different forces acted on this vertex. But we can also see it in a per element, or in an element-wise view. If I have an element, and this element has been extruded a little bit, and we can think of this element as pulling all the three vertices inside a little bit. And if we go over all those kind of elements and just add the force of the vertices together, then we have the forces on each of the vertices, on each of the vertex, right? Like the other element is pulling those two vertices over here. Then we know that those two vertices have the force pulling them inside, and those two probably will have the force on this edge, something like this. All right, so okay, so it's pretty good because we can think about each element as an individual, and once we have the force computed in each element, then we should be able to aggregate them together to get the force of the entire mesh. Okay, so it has 1, 2, 3, 4 points. Let's think about the first point. Because if we want to compute the force at this first point, F1, it's actually the energy E dx1. If this one has its index as x1, negative. Force is the negative of the potential, the gradient of the potential energy. All right, and because we know that, let me write it down. EI equals to this one, equals to WI multiplied by phi of Fi. And here, because I'm just considering this element I, I'm gonna omit this subscript I. So I'm gonna write it down as E equals to W multiplied by phi F for simplicity. I just don't want my subscription get exploded. All right. So now we can see that the F1, now F1 means the force acted on the first node. It becomes negative of dE dxi. All right. We can be more specific. It can be that because we know that F1 equals to F1 on x direction, F1 on y direction, and F1 on z direction. Let's think about it. Let's think about the force on x direction of the first vertex. Okay, it will become dE dx1 on the first dimension. So it's more like if this vertex is moving on x-axis a little bit, then my energy should respond on this vertex, and that's my F. Okay, we know that E equals to W multiplied by phi F, where W is a constant. It is only dependent on the rest post shape. So W is constant, just to pull it out. And the phi is a function that maps from R3/3 to R1. It's I can write it down using chain rule, dF double contraction dF dx1 1. All right, do you still remember that? This is a 3×3 matrix. This is a 3×3 matrix. I just applied chain rule on that. Okay, and what is this? We just go over it. All right, this is the first Piola-Kirchhoff stress tensor. So it's P. We know that we can compute this using P of F, using your favorite model. Just substitute F in, and then there we go. And what about this one? This one's a little bit more complicated. Let me expand it. So we know that F equals to ds multiplied by dm inverse. All right, and the ds can be written down as x1 1 minus x4 1, x1 2 minus x4 2 on y-axis, x1 3 minus x4 3 on z-axis, And the second column is x2 minus x4. And the third column is x3 minus x4, and multiplied by a constant matrix dm inverse. Here, only x11 is moving, because I'm only considering df dx11. We can think all of the other guys are constant. They're not relevant to x11. All right. So what does this mean? That means that simply df dx11, it's simply 1 0 0 0 0 0 0 0 0 multiplied by dm inverse, because only the first element is affected by x11, and the ratio it affects, it's a linear component. So it's once after taking the derivative, it becomes 1. Right. Okay. I can write down this matrix as a slightly better way. This matrix is actually E1 multiplied by E1 transpose, where E is a vector that it's a unit vector. It's 0 everywhere, but it's 1 on this ith element, and the zeros everywhere. So E1 is basically 1 0 1 0 0. So E1 transpose is basically this matrix. Okay, and we can do it all over all the vertices, all over all the dimensions again. So let's forget about the last vertex x4. Think just about x1, x2, and x3. What is df dxi and j? Where I means the index of the vertex, and the j means the index of the coordinate. All right. So let's think about it first. What is df dx1, say 2? If it's 2, then it's basically this matrix. All right, because it only have effect on here, and has no effect on the rest of the system. And this one, I can write it down as on E1, then E2 transpose and dm inverse. Is that correct? Let me see. Not really. It's E2 E1 transpose. E2 is 1 0 1, right? And multiplied by E1 transpose 1 0 0. And this one is this matrix. All right, the first row is 0, the second row is 1 0 0, third row is 0 0 0. All right, so we can generalize to any of those xi on j's dimension. It will become the ej multiplied by ei transpose dm inverse. Okay, this is good. And then the only thing that we need to do is plug it into the force formulation. And then we can compute the force for every point on every dimension. All right? Okay. Force. Continue. So, let's plug it inside. We know that the force acted on the first vertex, on the first dimension, equals to W multiplied by P, which is the Piola-Kirchhoff stress tensor, double contraction df dx1 1. And we know that this one is simply W multiplied by P double contraction EJ EI transpose dm inverse. Right. We can apply our favorite trick on that. We can convert this double contraction to a trace. So it becomes the trace of WP multiplied by this one inverse transpose. So it's dm inverse transpose EI EJ transpose. And then we can apply the cyclic permutation invariant law of the trace, move EJ transpose to the beginning of the equation. So it becomes trace of EJ transpose WP dm inverse transpose EI. We know that EJ transpose is a 1/3 vector. And here there are 3 matrices in the middle, sandwiched in the middle. It's 3/3 matrix. And here EI is a 3/1 matrix. So the total thing is a scalar. The trace of the scalar is itself, so I'm going to just get rid of the trace. It becomes EJ transpose WP. Oh, sorry, it's not EI, EJ. Let me get this one. This one is I and J because I'm already plugging the generalized form. It's applying on the i's vertex on its j's coordinate, right? WP dm inverse transpose. This one is ij. Transpose and EI. What is this one? It's basically a selection operation, all right? So the EJ will select the jth row of the matrix, and the EI will select the ith column of this matrix. So it becomes the matrix WP dm inverse transpose the jth row and the ith column. Right. There's one thing missing. This is actually the negative of the negative force, because force is the negative part of this one. There's the sign missing over here. Okay. So this one is pretty nice because we know this one is a 3/3 matrix. So we just need to compute it once. And the element there is actually, let me say, H is negative WPD inverse transpose. So this is my H matrix. It's a 3/3 matrix. And the jth row and ith column is actually the force on the ith vertex on the jth part, right? So actually H is basically F1, F2, F3. And what about F4? F4 is a little bit complicated because when we are calculating this one, taking the derivative of f over dx something, it will actually be something like -1, -1, -1, and 0, 0, 0, 0, 0, 0. And after the entire calculation, if you do it strictly in my way, then you can come up with the result equals F4 equals to negative F1 plus F2 plus F3. That makes perfectly sense because for one linear element, we want to also preserve the linear momentum of it. So the force acted on all 4 vertices together should equal to 0. Because by this inner force, it has there should not be any force to move the entire element to somewhere else, right? So it's a super intuitive to say F4 equals to just a negative of the summation of F1, F2, F3, right? So now it means that once you get an element, you can compute its rest shape volume. You can compute its current Kirchhoff stress tensor, and then the dm inverse transpose is something constant. Then you can construct this matrix and get the force on all 4 vertices. You can just loop over all the elements, and then you can get the force on all the vertices. Just aggregate them together, and then you can do explicit time integration, right? And in the original course note, the pseudocode is something like this. So there is a pre-computation step. In this pre-computation step, they just compute dm, the rest pose edge matrix, and dm inverse for just the inverted at the first, because you just need to invert it once. It's only dependent on the rest shape, and also calculate the w, which is 1/6 of determinant of dm. That's the volume. And when you want to do the simulation, you want to compute force, the first thing is you can just calculate the current shape edge matrix, ds, compute the f equals to ds multiplied by dm inverse, and substitute it into your favorite material model. You can put it as a co-rotated linear elasticity model, or you can think of it as a Van Kerckhoff model or Near-Hookean model, whatever you like. Get the P explicitly, and then you can construct this H matrix. All right. After you construct the H matrix, it's basically saying H equals to F1, F2, and F3, and F4 is the negation, is the negative one of summing them together and add it to the last vertex, and that's done. And you can just loop all the vertices and then calculate the force on all the vertices, and you can loop all the elements and loop and calculate the force on all the vertices, and then it's done. It's the explicit time integration. All right. For the implicit time integration, it is more complicated because you also need to take the derivative over this P if you want to do the implicit time integration scheme. You also need to take the derivative of dp df. Whereas this one, it's actually a four-dimensional matrix. You can think of it as a 3 by 3 by 3 by 3 matrix. It's a four-dimensional one. If I want to flatten it down, write it on my paper, it's a 3 by 3 matrix, but each block is another 3 by 3 matrix. All right. So if you're really interested in that, you can go back and do your homework to do the dp/df by yourself. And if you really have questions, you can go back to me. Trust me, it's a little bit more complicated than you think, because it goes to high dimensional system. It's really easy to get the index wrong. All right. Okay. So I think now I just finished everything about simulating finite element system, at least using a not very stable explicit time integration scheme. That's it. Do you have any questions on that?
So does one generally have to use the implicit form because you said it's unstable for the explicit, or?
So not really. Actually, in mechanical science, people are just using explicit forms, but with really tiny time steps, and dampen a little bit, then it won't explode. It's just the trick to do that, right? Implicit form is nicer to implement. You need to construct the Hessian of all the elements too, and and Ladislav will tell you about one thing called projective dynamics. It's a work that we collaborated with EPFL, that also Sophia in EPFL. It's in projective dynamics. You can also simulate at least the co-rotated elasticity model without calculate the Hessian explicitly, and you can reuse the Laplace. You can kind of like approximate your Hessian using your Laplacian matrix, which is a fixed if you already discretized the entire mesh, and use that one to go for your optimization method, and that will make the material to be simulated in a very stable way, but also in an implicit way, right? Okay, great. Okay, thank you very much. Next week we already collected your final project proposal. So next week there will be one class telling you about fluid simulation, mainly about flip and position-based fluids, and another class about how to do fracture. Right. Okay. Thank you very much.